In 9.3, we're continuing to looking at trig identities and different equations. So we're going to be doing similar processes to other sections of proving identities, simplifying, but also pulling in our unit circle and doing a couple of things. So the first thing I want to do is look at using our double angle formulas to find exact values. And so what we're going to be doing is we're going to use our sum formulas from the previous section, and we're going to let alpha be equal to beta. So I want to show you a proof of this sine one, and then the other proofs will follow suit to this. And so what we're going to do is we're going to let alpha equal beta, and we're just going to call that theta. So just let's look at this. What if alpha and beta were the same angle? So I would have sine of theta plus theta. So I'm going to call it a new letter. So using this summation of sine, I would end up with sine theta, cosine theta, plus cosine theta, sine theta, but multiplication is commutative. So over here I would have two thetas, combining like terms. Over here, whether I wrote sine, cosine, or cosine sine, those are equivalent. So I have two of them. And you can see that if I have sine of 2 times an angle, that's equivalent to 2 sine cosine. And so the proofs of cosine and tangent would follow the same pattern of just substituting values we know. We look at maybe calling them the same angle and how that would work once we get the same variable. And then we get some double angle formulas. So you'll notice here that the double angle formulas can be summarized as, here's our sine one that I just showed you. Cosine is unique just because of the way it kind of falls out. We could use that it's equal to cosine squared plus sine squared. We could also make some substitution with Pythagorean identities and maybe call that 1 minus 2 sine squared. Or again, another substitution of the Pythagorean identity and call this 2 cosine squared minus 1. These are just options. It depends on our purpose. What are we trying to turn the left and right side into? What's our final destination of this? Are we trying to get it in all terms of sines? Are we trying to get it in all terms of cosines? What are we trying to do? So we'll kind of see these three as we move forward. And then tangent of 2 theta is equal to a 2 tangent theta over 1 minus tangent squared theta. And again, these proofs kind of follow suit and are recognized in your textbook. So we kind of got some steps to get us going. We're going to give in the tangent of an angle and the quadrant in which it's located. That's important. You're going to see that as we draw triangles. Use the double angle formulas to find the exact value. So kind of some steps along the way. Draw the triangle. I can't tell you that enough throughout trig to reflect the given information, because wherever the triangle is in relation to your quadrants or where the angle is, gives you a lot of information. So draw it out. Determine the correct double angle formula that you want to use from above. Substitute values into the formula based on the triangle, and then simplify it up. So let's kind of look at some of these options. I've got A, B, and C kind of portioned out here. And so we're going to look at this example, but we're going to kind of look at all three of them. And so they say, given that tangent theta is equal to -3/4, and theta is in quadrant 2, find the following. So the first thing I need to do is I need to draw this out. So let's think about our coordinate plane. Here's quadrant 1, here's quadrant 2. And it says that this angle is equal to -3/4. Now remember from our shorthand here of SOHCAHTOA, then I'm going to say, well, tangent is opposite over adjacent. So this ratio here of -3/4 is opposite over adjacent. I'm in quadrant 2, so that means I'm going to be drawing a triangle here in quadrant 2 because you want to base it off of the angle that it's creating. And since I'm in quadrant 2, I could tell you that this is going to be +3 and -4, so that when I'm looking at theta, opposite over adjacent gives me that equivalent. And I knew that it was a +3 because I'm going up with my triangle. This is your negative x-axis, so I knew -4 needed to go here. Now, based off this information, we could use Pythagorean Theorem. And we could say -4 squared plus 3 squared equal to c squared. And so this would help me to see that c is 5. You want to square these, add these up, square root them. You're used to the Pythagorean identity at this point. And so now I've got all sides of my triangle. That being said, I know a little bit more information. That sine of theta, again, this goes back up to sine is equal to opposite over hypotenuse. This would be equal to my opposite, 3, over my hypotenuse, 5. And cosine of theta would be equal to my adjacent over hypotenuse, so my adjacent over hypotenuse, so -4 over 5. So I'm just trying to get all my building blocks before I kind of start running through this problem. So part A, I want to look at sine of 2 theta. Now I can't just say, oh, I'm going to take theta, multiply it by 2, because I don't actually know what theta is. I want to figure out what this is equal to in terms of ratios. So I'm going to use my formula to know that this is equal to 2 sine theta cosine theta. Again, that formula is from our previous page and proof. Giving me 2, I know what sine theta is. We already found it up here, 3/5. I know what cosine theta is. Again, we already found that up there, so that gives me -4 over 5. Then we just need to compute our arithmetic from there. So multiplying this all together, we get -24 over 25. So what we were able to do was to base information that we knew from the given problem, get all of our foundational pieces, and then use our formula to compute from there. Let's look at cosine of 2 theta because its formula is a little bit different. So cosine of 2 theta, that's equal to cosine squared theta minus sine squared theta. Remember, we had 3 really options on that one, and so I'm going to use this one because I know about cosine and sine from kind of our building blocks that we got up here. So let's see, I'm going to take my cosine, which is -4 over 5, and I'm going to square it, minus my sine, which is 3 over 5, and I'm going to square it. Again, now we're just down to arithmetic of our fractions. So this gives me 16 over 25 minus 9 over 25, and combining that together to give me 7 over 25. So you can see that our building blocks paired with our formulas are able to really output these ratios that we are looking for. Now tangent looks a little bit trickier. When I'm looking at tangent of 2 theta, this would be 2 tangent theta over 1 minus tangent squared theta. So this gives me 2 tangent theta. Now tangent theta was given in the problem. That's -3/4 over 1 minus -3/4 squared. So you've kind of got a little bit hairier arithmetic to work through on this one. This would give me -3 over 2, 1 minus 9 over 16, and that all simplifies down to -24 over 7, which really makes sense for this problem because we're working with cosines and sines along the way. And you can see that all these ratios are very similar in the values that are in their numerator and denominators. And so when we're working with these double angle formulas, I feel like the struggle is going to be if you don't get your building blocks and if you are outputting or working with your arithmetic incorrectly. So make sure you have the tools that you need before you get going. Now here's another problem that we have, and it says use the double angle formula, the ones we've stated, for cosine to write cosine of 6x in terms of cosine of 3x. And so what I'm going to do is I'm going to start with cosine of 6x, and I'm going to work over till I get to cosine of 3x. So consider cosine of 6x. And this would be the same thing as cosine of 3x plus 3x. I just kind of unadded them. I want it to do that because I want it to go back to my sum formula. So think about this. This would be cosine of 3x, cosine of 3x, just adding those two together, minus sine of 3x, sine of 3x, because we're considering this like cosine of alpha plus beta, but my alpha and beta are the same. So that simplifies down to cosine of 3x squared minus sine of 3x squared. And so I have it now in terms of cosines of 3x. And so I kind of want to show you this proof because it kind of takes into the fact of the proof of how we can get our double angles to work out as well. Next ones is I want to use using the double angle formulas to verify some identities. So this is going to go back to what we were working with in order of verifying identities in previous sections of you want to choose your more complicated side in order to rewrite the maybe more simpler side. So you can see here that this looks a little bit more complicated than this side. And so I'm going to be starting with the right and moving to the left in this example. So I want to work with sine theta plus cosine theta squared. And I want to eventually get to this part of the problem. So what I'm going to do is I'm going to multiply this out. I'm just going to multiply the binomial or FOIL method if you like. And so this would give me sine squared theta plus 2 sine theta cosine theta plus cosine squared theta. Now, cleaning this up a bit, you could maybe put your squared terms together to see it more clearly what you're working with. So I'm just going to rearrange. You can see that these together would give me 1 plus 2 sine theta cosine theta. And if we reverse one of our properties, we know that 2 sine theta cosine theta, from our very first proof of working with these, is equal to sine of 2 theta. So here we had the Pythagorean identity, and here we had that double angle formula going backwards on the equals. But I was able to accomplish going from the right side here over to the left side. So again, your same attributes apply here of being able to start with your complicated side and then move to your simplified side. So part 3, what we want to do is use our reduction formulas to simplify an expression. So we're going to get some new formulas in part 3. And so I've just kind of stated them here for you. And again, the proofs of these are in your text, which you can find within Canvas. And so let's kind of review them. We can see that now we're working with sine squared, cosine squared, and tangent squared, and turning them into a power reduction formula, actually, because you can see that we no longer have a squared term in any of these. But you can also see that all 3 of them go back to cosine of 2 theta. So it makes sense that they kind of follow suit of that double angle one because these are outputting double angles. And so what I want to do is I want to start with this example here and show you how these will be beneficial to us. So you're going to see that if I start with cosine to the 4th power, and we want to turn it into powers of sine and cosine of powers not greater than 1. So basically I want to get it down to very simpler terms. And so I'm going to start with this to the 4th power. So the first thing that I'm thinking of is this equivalent to cosine squared, the whole thing squared. And the reason I want to do that is because I know this information up here. I know that cosine squared theta is equal to this. So it's getting in that right path of getting down into singular cosines. So I'm going to substitute that formula in, and that gives me 1 plus cosine of 2x over 2 squared. Then I'm actually going to square this thing out. So the first thing I'm going to do is I'm going to square this 1/2 or division by 2, and that's going to give me a 1/4. And then I'm just looking at FOILing out or multiplying out the 1 plus cosine 2x times 1 plus cosine 2x, which yields me 1 plus 2 cosine of 2x plus cosine squared of 2x. So this looks good, and the last thing I need to do is reduce this cosine squared down in a way. So I'm going to go ahead and distribute this 1/4 because I've got a whole lot of parentheses going on. So that gives me 1/4 plus 1/2 of cosine x. And again, I'm just distributing that 1/4 out plus 1/4 of cosine squared 2x squared. And then I'm going to use my power reducing formula again here. But note my theta is 2x. And so if my theta is equal to 2x, when I do 2 theta, I'm looking at 4x in my output. So I have the 1/4 plus the 1/2 plus 1/4. Now I'm going to make my substitution here of cosine squared 2x, and that would be 1 plus cosine of 4x over 2. And then when I start simplifying this up, again, just bringing down the front 2 terms, this yields me 1/8 plus 1/8 cosine of 4x, putting the 4th and the 2 together to get those 1/8. So here's your 1/8 plus 1/8 of cosine 4x. And then combining like terms accordingly. So it gives me 3/8, this 4th and this 8th. So 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x. And so again, we were making this substitution here. That's why we're all of a sudden having a 4x. And we got this down into terms of cosine or sines to the 1st power. So this one was a little bit more complicated because we've got some fractions floating along there, but we also have that reduction formula being used twice.